So now that we know how rocks form, we're going to talk about how they break down. This chapter covers weathering, erosion, and soil. So weathering yields the raw materials for both soils and sedimentary rocks. Some weathering processes bring about physical changes in earth materials with no change in composition. It's going to be called mechanical weathering. We'll talk about that. Some weathering processes cause change in the chemical composition of the parent material, and that's chemical weathering. A variety of factors are important in the origin and evolution of soils. These include climate, the parent material being weathered, the amount of organic material, and slope, among others. There are other factors as well. Those are the main ones. Soil degradation involves any loss of soil productivity that results from erosion, chemical pollution, or compaction. So here we see a picture of granite, and you see that it's been weathered. It doesn't have angles on it, they're rounded, and obviously things have gone into solution and washed away. The bottom picture is basically mechanical weathering by a human, where a human took some granite and seems to have broke it up with a hammer or something like that. Rocks and minerals disintegrate and decompose just like everything else, and the process is, like I said, mechanical and chemical weathering. This would be physical in the sense that somebody's taken a hammer and crushed the rocks. But the real question is what happens after they're weathered? Because weathering and erosion are different things. Weathering is the mechanical or chemical alteration of the earth, I mean breaking it down or changing it in some way so that the surface is changed. Erosion involves moving those materials somewhere else. And usually this is done by water. But wind and, wind is primarily the other erosional force that moves these materials around. So this is a picture of probably Arizona or Utah, somewhere in the Great Basin or out west where it's desertified. And what you'll see here, grab a pen. What you'll see here is there are several layers. A layer there, and there are layers in this rock as well. And you can see in the bedding plane, that's the area where the layers are sort of drawn out. Like right here is a layer, and there's another layer right there. And each one of these layers has different hardness associated with it, depending on how it was laid down, what material was washed over this. This was probably a shallow sea or something. Many millions of years ago. If it's in the desert southwest, which would be Arizona, it could be anywhere from 60 million years to 100 million years old. Some of those rocks, some of those canyons in Utah are up to 1 billion years old. In other words, weathering and erosion take place at different rates, and not all rocks weather the same and erode the same, which means that rocks aren't structurally the same. So you see that when you look at rocks, they have different minerals in them, and those different minerals will weather and erode at different rates. In this case, this is a picture of a desert, and the mechanical processes for erosion, or actually for weathering, are frost in the desert. Believe it or not, most of their water comes as snow, and there's a water gets into the crevices and then it freezes, and because water is less dense when it's frozen, it fractures and causes things to pop out. It's a pressure release. Then of course there's thermal expansion and contraction related to the sun, because it is a desert. It happens here in Michigan too. And you get crystal growth of other things that we find in deserts, like calcium carbonate or salt, which would be sodium chloride. And then of course we have activities of the plants and the animals or organisms that are on the ground and around these rocks. One big idea that you need to remember about mechanical weathering is that when products of mechanical weathering are sitting on the ground, they are chemically the same as the parental or parent material, in this case the parent rock. And sedimentary rock can weather and then reform more sedimentary rock as it moves down towards sea level. So here we have an image of mechanical weathering disaggregation of Earth, or of the Earth. And basically it's water action. Water freezes and gets into the cracks, and then it expands, which causes rocks to pop off. These are fractures in the rock called joints because they don't travel through many different bedding planes. They don't go very deep, so they're cracks in the rock and they are not faults. The activity of the frost makes the cracks wider, and then this happens, several thousand times in a day because it's happening on a very small scale. One reason our roads are so terrible in Michigan is because we are in that frost heave zone where it thaws out during the day multiple times and gets cold, and it's right at the level where the water is almost frozen, and then it freezes, and then it thaws out, and then it freezes again, and so you have a lot of this activity, and then cars come along, and when these rocks are popped out of the asphalt, they get knocked away, and you get these big holes. If you remember from when we were talking about the different sedimentary rocks, this material, as it breaks off due to frost action and aggregates at the bottom, we normally call this talus. We form a talus slope, and this would be basically an accumulation of rock that has gone through physical or mechanical weathering. Chemical weathering, which you see on this slide, is a little different. Joints form in response to a pressure release as a result of, well, salt formation or something that's going to get into the rock and change the way its chemistry is, or the way it looks. So the surface is actually chemically changed. But in order for the chemistry or the salt or whatever is going to fracture these up, they go through a mechanical weathering process first. So we'll get to the chemical weathering, but in this case, you have thermal expansion and contraction of specific areas, so that you get huge joints going deep into the earth, and as these rocks expand due to either pressure release or some other factor, extreme heating and cooling. In Texas, when I lived down in San Antonio, I would get in my car and the thermostat in my car would say 130 degrees because there's a urban heat sink is what they call it, because they paint everything with this sort of black tar substance so that the roads themselves are they're much softer than the roads we have in Michigan. They're full of tar, so that when they expand, they don't do this kind of stuff. This is actually a rock hammer that they're showing you how high this actually bowed because of expansion. And then this is just sheets of rock will come off this area as they expand and fracture and slide off down. This is probably a dome. I will reference the growth of salt crystals, and the growth of salt crystals is similar to the growth of ice crystals. It'll cause the rocks to crack and pop off just like frozen water or ice, and that is actually not a chemical change. It is still mechanical weathering, or considered mechanical weathering. Then, of course, in this slide you see organisms, and organisms contribute to both mechanical and chemical weathering. They produce organic acids that go in and break down the rock. Lichens, they have lichens on here, but the fungi that form associations with the trees, which means these mutualistic fungi, actually they penetrate the rocks by digesting them. They actually will go through crystals of biotite because they're looking for phosphates, or phosphorus, actually not phosphates. They're looking for phosphorus or other sort of potassium, calcium, whatever the tree needs, and that fungus will turn over those nutrients to the tree, and in return the tree will give the fungus sugar so that it can survive. And these fungi that live on the tree roots, or actually most plants' roots, are they don't break down wood. They don't have the ability to do so. So they rely on the plants to get them food, and the plants rely on them to get them nutrients. And without either one, these plants would not be there. So we wouldn't have trees living on land or other plants. But not only do they contribute to the chemical weathering by breaking down the rock, they also expand and contract through a pulsing action. And tree roots do the same thing when they grow. They grow in a pulsing action, which means they swell a little bit, fracture the rock, and then they reduce, and they get in a little farther, and they swell a little bit, and that's how they break up the rock. And actually, soil is produced quite rapidly this way. Without plants and animals, soils would take a lot longer than the 1,000 years that it takes to make 1 inch of soil as it does today. So, which keep that in mind when we talk about erosion. In this slide, we see chemical weathering and decomposition as a result of probably lichen. That's what I see on these rocks. And then the lichen produces these organic acids that get into the smaller rocks, like right here. They'll get into this rock, this crack, sorry, right here. And there's one that's getting a little bigger, and they start actually just dissolving the rocks so that you get these sort of voids, what we call them, voids in the rock. And this process is usually mediated by rain, and what it does is it gets nutrients that can go into solution through an acidic process. We call water the universal solvent because it dissolves pretty much everything that can dissolve in water that's not hydrophobic, and that's because water is the smallest polar molecule that we have on Earth, and it is very efficient at getting into between the lattices of specific crystals. You know about sodium chloride, also calcium carbonate. It's a little less soluble, and then we have, which is calcite, but they all will break down in the presence of water. But water also has carbonic acid in it because the CO2 that's in the air dissolves in the water as the rain falls, making it slightly acidic, which means it increases the ability of the water to actually break down rocks. And chemical weathering is basically the decomposition of rocks and minerals by alteration of that rock face through a chemical process. And unlike in mechanical weathering, which is a physical process, this is where we're actually changing the mineralogy of the rocks. And so I want you guys to think back to when we were talking about magma chambers. That's a chemical process. That's chemistry. When those rocks develop as a result of the mineral precipitation, that mineral precipitation is a chemical reaction. In this case, it's the reverse of that chemical reaction, or the changing of the chemistry, where you're breaking down certain feldspars into clay and releasing CO2 or carbonates into the solution or into the air. One thing you should keep in mind is the decomposition of rock is facilitated by the kind of environment in which you find those rocks. And this kind of decomposition here is obviously a desert, so it's not going to be very rapid. But if you go to a hot and wet environment like the tropics, obviously, it's going to accelerate chemical weathering so that you break down rock very rapidly. So in this slide, I'm showing you basically what I just alluded to. And what we know about water is it's this really small polar molecule. And what that means is if you look, there, the oxygen side, since the nucleus of oxygen is so large, it pulls or attracts these electrons that are around the hydrogen to its side, which means you accumulate, or it's a cumulative negative charge on one side and a cumulative positive charge on the other, and we call that a dipole moment. You don't have to really remember the dipole moment to know that water is a polar molecule. It's a very small, the smallest polar molecule that is very prevalent in nature, and what it does is it interacts with the, well, in this case it would be sodium chloride because there's the chlorine and there's the sodium. It interacts based upon whatever side the water is pointing towards specific elements. In this case, because we said that the negative side is over here and the plus side is over here, these hydrogens are going to interact with the chlorine, and the chlorine is actually going to be more attracted to the water rather than staying in the crystal lattice with the sodium right here, because sodium is much smaller than obviously the water molecule right here. And you end up dissolving salt in water, and we call it the universal solvent. We call water the universal solvent because of that. The important agents of chemical weathering are the presence of oxygen, which is an oxidizing environment. There's carbon dioxide, which gets into the water and produces carbonic acids. Then we have acids produced by organisms and other chemistry that's freed up when the rocks dissolve. For example, we have calcite, which you guys have in your collection. You've put it's in limestone, and it's nearly insoluble if you have a neutral or alkaline, which means a basic solution, not acidic, and it doesn't dissolve. But if you add an acidic solution to any of that rock, it rapidly breaks down, and the atoms, dissociate. You get carbonic acid forms, CO2 comes off, and then the presence of other acids from organisms or from acid rain or whatever accelerates the process, and you can break rocks down pretty rapidly. This is pretty evident when we make tombstones out of limestone or quartz type of, quartzite or something like that. If you go out to the East Coast and you look at those really old graveyards, you'll see gravestones that are almost completely gone if they were made out of limestone, and ones that were made out of more resilient material are very easily read. So I asked the students in the face-to-face class to describe what they see in this picture, and it's a sandstone. Obviously, I'm looking at the idea that the rocks rust, and whenever we look at really old soils, in this case, this is again probably Utah or somewhere around there, and this is going to be on the order of maybe 100 million years or whatever. These soils that produced this sandstone are oxidized, which means that they were exposed for a long period of time on the surface. Now remember, when we see red, it's not necessarily just oxides. In this case it is, but sometimes it can be aluminum exposed as well because it's aluminum oxide. But aluminums will turn red as well, along with the iron, which basically means that the rocks rust and they dissolve like your car. Here's an example of chemical weathering and decomposition in feldspar. I said I'd show you a picture, and this is called hydrolysis because it's using water to cut or to break apart a certain bond or chemistry. So we call this hydrolysis, meaning hydro being water, lysis to cut. So this is water cutting. And what you see right here is the water, and that's going to do the cutting. You have some carbonic or bicarbonate, which is actually a buffer, and you have some acidic, something is causing an acid because you have these hydrogens available. And then what it does is water will break, and you get the OH, which is, if you notice, you have H2O. It looks like this, right? And if you take this H off, you have an OH, which is what you have, whoops, right there. And this is a clay now, so it's kaolinite, and it's a silicate clay. And this is the stuff that we find all over the place, and it breaks down very small, and you end up releasing a bicarbonate atom and then a potassium. And potassium's, well, very water soluble, and you break down the rock. Another factor besides the presence or absence of acids is the surface area to volume ratio. Surface area increases, you end up getting more chemical activity. And as I told the students in class, that's why we chew our food. We chew our food so that we can make more surface area available to the enzymes that we're mixing with our food so that our food digests much better than it would if we just try swallowing a piece of steak without chewing on it. I mean, it doesn't go down very easily because we haven't evolved to actually eat food without chewing it, where dogs, which is very interesting, their stomach acid is different. They don't chew their food. It actually messes up their digestion. because I don't know why, but they actually don't chew as much as humans do, and they will gulp their food, which is kind of interesting. I have labs, so they more than gulp it, they just inhale it. The idea here is that you will have mechanical weathering that's fracturing the rock, creating joints, which breaks the material into smaller pieces and increasing the surface area for chemical reactions and more fracturing as these chemicals weather the surfaces. More surfaces exposed, the faster the weathering. So if you look at this table 6.1, if it's still 6.1 in the book, I don't think it's 6.1 in the new book, but this is the old book. This is just a reverse of Bowen's reaction series. So it's an inverse of Bowen's reaction series, so the minerals that form first that are more stable at higher temperatures, or actually go through their chemical reaction at higher temperatures and become solids as they crystallize, are the ones that actually break down first. So the stability of the igneous materials or minerals is a reverse of Bowen's reaction series, or an inverse. Quartz is obviously the most stable, and I think I've mentioned this before, but sand, or quartz sand, only breaks down so small and is much less susceptible to chemical weathering. Whereas olivine is the least stable. You have the feldspars and all that kind of stuff that I just showed you how they break down. The potassium feldspar, the K spars is what we call them. They dissolve in water if there's some acid present. Which leads us to this slide, which I find very interesting. Spheroidal weathering is a result of surface area. So if you look at how the mechanical weathering works, we're breaking off, just pretend they're square or rectangular pieces, and if you look at a point, in this case they're showing you the point here, there are 3 surfaces to weather, and as they weather they become, these cobblestones become spherical, and as they become spherical they actually weather more slowly because there's less area exposed, which is kind of interesting. Angular rocks tend to be round by the time we find them if they've undergone any kind of weathering and erosion, moved around and bumped around on the bottom of a stream or whatever. Which leads us to the breakdown products of weathering and erosion, which is our soil. And our soil comes in a variety of layers. Actually, not a variety, there's a specific set of layers, but the layers are weathering products from the Earth's surface. And it includes anything from sediment, weather material from the streams, and things that brought in by erosion, wind, dust, and also organic material and other material that is brought in by organisms. So the soils obviously are support plant life. They contain something called humus. It's not hummus. You don't want to eat this stuff. It's an organic debris from decayed organisms. It's resistant to weathering, and it usually is deposited by plants. It also protects them from other invasive organisms, specifically diseases, by changing the pH of the soil so certain fungi or certain bacteria can't live where they're living as they produce these acids or bases, depending on where you are. Usually soil contains clays, sand, and silt or other mineral matter. We're going to do a soil column using the 100 mil graduated cylinder that you have, and you'll use the soil that's around your house, and we will be able to compare and contrast soils. We'll put it on a soil triangle so that we'll be able to identify the kind of soil that you have. This works sometimes. Sometimes there's too much organic material in there and it doesn't separate very well. But I'll do a video so I can show you what that would look like. Now onto the slide. So in soils we have a lot of air, a lot of water, and then of course a lot of mineral particles. So most of the soil is just weathered and eroded rock. We do have an organic layer and organic material in the soil. In this case it's 5% of the total soil mass, and most of it is plant material from these what we call intermediate organic acids. You don't have to remember that, but it's called humus. Then you have the living roots. You also have fungi, you have nematodes, you have a bunch of other organisms that are around those roots. And overall, the soil is one of the most complex chemical soups that we have going for us. And it's because that's what gives us life. It's also where animals and plants do all of their stuff, meaning they pick up nutrients or they dig around in it, they make homes. I mean, there's just a wide variety of issues, not issues, but things that the soils offer us. The soils are actually broken down into specific layers, and we're going to talk about those layers next. And they are basically the same in every soil. You'll have these specific layers. And here they are. So on the top you have an organic layer. It's like loose leaves and organic debris. Underneath that you have partly decomposed organic debris. It's still the OA interaction zone. The topsoil is the stuff, if you go out by the college right now, they dug a big hole in the ground. Our topsoil is really deep in Michigan. It goes down several feet. And then there's a dark layer and then a light layer. So the topsoil, dark in color, rich in organic matter. Then you go down to the zone of intense leaching or alluviation. It can be pink, it can be dark colored. Usually it's sort of it looks like a white powder. And then you go into the subsoil zone of accumulation where you get all sorts of stuff percolating up from the bottom and stuff weathering down from the top, which means water moves stuff around, and you get a lot of iron deposition things in there. You get a transition zone, which is the C zone. It can be labeled, it depends on who you talk to, it can be labeled D. It's also labeled some depending on who decides to label it. But in this case, we're just going to call it a transition zone. And then partly weathered material is C, and the parent material is sometimes called D as well. And there's pretty much the same soils no matter where you go. So we have a thin layer of humus, partly decayed plants on the O. The A horizon is the topsoil. That's usually the fertile soils, is where we plant our food or plants that we're going to eat. More organically rich than any of the other horizons. Most important layer for protecting for future generations so that we can grow stuff. Then there's the B horizon. I guess if you're protecting the A horizon, you're protecting the B horizon. That's the subsoil. It's a zone of accumulation for all sorts of stuff. In many ways, fungi that form these associations with the plants digest these aluminosilicates, because that's most of the rock that we have on the surface of these continents, and they actually remove the aluminum and deposit it in the soil in what we call an intermediate weight organic acid. And we actually will find these old soils, we call them bauxite. It's not all fungal action, it's actually percolation and alluviation. It's the E zone, and it's good for all sorts of, we get aluminum foil from a lot of the bauxites. We also utilize it for other mineral resources, or we utilize it as a mineral resource. And then, like I said before, you have the B zone, which is, the C zone, which is partially weathered, in-place bedrock. It look like regolith, which is what that stuff that falls off the side of mountains and makes talus slope. That's what it would look like. Not all of these layers are in every soil column. We use them to describe soil columns, but sometimes you'll be missing a B layer or an E layer. E is probably the least common, the one that's mostly missing from most soil columns if you're going to look for specific columns in the soil. That's why it's E. It usually goes A, B, C, and then they'll add E if it's there or not. And here's a profile of latitude. And if you look, let me get a pen so I can draw some stuff. If you look, the tropics have a very deep soil, but their actual organic layer up here is it's only like 3 millimeters thick, which means that most of the nutrients, when we look at tropical forests, is in the living tissue. There's documented cases where limbs have fallen off, landed in the tropical forest, and they're gone within a couple days. Where in Michigan, if they fall off, they're around for a year, if not longer. Then you move to the deserts, which don't have a lot of water, but they have higher temperature. And if you'll note, most of the areas where we have soil, it's due to plant activity and the ability of organisms to grow and do what they do. So the desert's obviously too dry. The temperature's fine, but there's so little water that the organisms, they look like cacti. Or if you go to the Gobi Desert, they'll look like euphorbs, which is not a cactus because cactus are only found in the desert southwest. Unless, of course, they're in a potted plant. If they're in a pot somewhere. And then you have the deciduous forest, and then you move up into the boreal zone, which the soils in the boreal zone, they're usually a little deeper than the stuff in deciduous, so I don't necessarily agree with this figure all that much. They're pretty deep in the evergreen forest because the evergreen forest produces oils that are acidic, preventing the breakdown of their leaves, or the needles. We call it their leaves, but we call them needles. And it gets pretty thick. It can get up to a foot thick. Or if you go to the coast of Oregon, it can be 3 feet thick. I've had to dig through 3 feet to look for roots and other things. It's pretty thick. You go to the Arctic, obviously, where there's no water here, because it's not available because it's too dry. There's no water here because it's frozen. So the plants can't really grow very long. It's too cold, and there's not a lot of available water. We call it bioavailable, but there's not a lot of water available for these plants here. And in most cases, climate is the factor that determines how much soil you have and what it's going to look like. So in this slide, we have, well, Michigan, deciduous forest soil, and you have coniferous forest soil. They're humid forests. Well-developed day horizon, which means it's really thick. I'm really surprised how they drew this because usually it's thicker in the evergreens. I don't know if they're maybe, well, I don't know, it's pretty thick in the deciduous forest here in lower Michigan, but I guess it depends on where you are. If you're on the coast where they get a lot more rain, these are acid litter and the humus is much thicker in the evergreen forest. But they have iron and aluminum rich B horizon, which is this alluviation zone, and you get a really bright light grayish brown silt loam, light colored, and acidic layer here. In the deserts, it's a little different. They call them hot desert soils. They have a very thin organic layer because the trees aren't really the cacti aren't dropping a lot of the leaves because they want to hold on to them because they're very expensive to make when you don't have a lot of water available. And they tend to have a B horizon that has a lot of irregular masses of calcite. We call it caliche because the soils are alkaline. It's calcium carbonate. And it's calcium carbonate because of the drying. We call them playa lakes. That's what I was trying to remember. We call them playa lakes, and they often dry up and leave behind all the salts that were in there. And most of the salts in the desert southwest, or much of those salts, are calcium carbonate up at higher elevation and calcite in the soil, because the sodium chloride is so soluble that it tends to go down to the lowest areas. In this case, would be the Great Salt Lake if you were looking at the desert southwest, or the ocean, which would be the point of sea level. In this slide, this rock has been turned over. It appears if you turn over rocks in the desert, they have caliche on the back side of them, so that's calcium carbonate or calcite. And then the picture on the right, it looks like hardpan. It's probably a reg. An erg would be dunes. This would be a reg, so it would be something like desert hardpan. That the white material surrounding everything is going to be sodium or calcium carbonate. This is probably a sodium carbonate because there's going to be a lot of sodium chloride or chloride available in this area. It'd probably be, I don't know, somewhere in, it's got to be Nevada because this is what Nevada, I see some basalt, and there's a lot of basalt in Nevada, probably north. Fallon, Nevada, probably near Idaho. I think in the book, yeah, let me look. Yep, it says Fallon, Nevada. So yeah, it's got to be, it's up north. So pretty interesting bedding plain. If over time this will end up becoming sedimentary rock, it'll just take a very long time. It's possible that you can get big enough lakes to develop big deposits. In most cases, the big, huge calcite deposits come from shallow seas, not necessarily these lakes. And here we have something that looks like bauxite. It's a lateritic soil, so there's going to be a high level of chemical weathering. It's probably going to be in the tropics. Have a lot of iron and aluminum in it. You can mine this and make aluminum foil. My daughter used to call it aluminum voil. I don't know why, but anyway, that's why I remember when I look at these pictures. And this is going to be a tropical region. I don't know if I look in the book, it says it is from Madagascar. Yeah, so this is going to be an area where they get a lot of rain, it's warm, and there's some intense chemical weathering going on in these soils. Because when you look at laterites, they are formed in the tropics. They have very infertile A horizons because they don't have a lot of organic material that's going to get through, or it's going to get washed through rapidly. So rapid decomposition due to the activity of animals and plants does not facilitate agriculture because the A horizon, the O horizon is almost non-existent. The A horizon is very thin. And all of the soluble ions, as it says in the picture, leach out. They go away. Most of the nutrients are usually in the living biomass, so what happens is if we cut down the tropical rainforest, we try to plant corn, it lasts all about 2 years and you get this hard pan, iron oxide developed that just you can't, I mean it's as hard as concrete. You can't do anything with it until the forest moves back in and reestablishes itself. Other factors that produce soil or control soil formation are the type of parent material, if there are obviously presence or absence of animals or plants, relief or steepness, geography of the slope on which these soils are forming, and then of course time. One thing that I stress to most of my classes is it takes about 1,000 years to make a good 1-inch layer of soil, and I mean that's the A horizon in which we do all of our farming. And we know that we're losing this soil at 3 inches a year. We do have really thick soils in the Midwest, but they can go away. And in fact, I think we're producing 30% less food than we were in 1950 because of abused soils. Which leads us to this slide, which is talking about soil degradation. In this case, the farming practices that you see before you in this picture are pretty good. There's contour farming going on, and they're doing what they need. They have different crops. They're between, I don't know if it's like wheat and I don't know what the green one is, but they have different crops that are planted right next to each other, so it prevents the monoculturing, straight lined, straight rows, which facilitate erosion. One thing that I find interesting is my parents live out in Colorado and they have expansive soils, and I have a bunch of information on expansive soils in the notes, but expansive soils are pretty hard to farm on because they don't have a lot of nutrients. It's primarily clay, and it can expand up to like 6% in one day, or a couple days, probably a couple days. It'll rain, and on their farm, you'll see cracks develop over the summer that go down 4 or 5 feet, and they're pretty wide. They're 3 or 4 inches wide. And then when it rains, those expansive soils will move, fill in those cracks, and actually expand like 6 inches. One concern we have about expansive soils is if you get a lot of rain, they can actually crush houses because they don't have anywhere to go. And, well, they don't crush them, they crack the foundation. So you want to avoid areas where you have a lot of expansive soils. But out west in Colorado, it's the only place you can build a house is on those soils because they're the only thing that's there. So you got to drive pylons in 32 feet, I think, rather than 16. The one that we usually do around in most places, I think it's 32 feet. And it's pretty expensive to build houses and keep them level. Although my house is kind of not level in Michigan because I don't have any pylons in my house stabilizing it. And we do have clay soils. Or actually, we have clay in the soil. This slide shows you extreme degradation where you actually have gully forming in probably one season. And it starts like this where you get rills. And then the rills, which is moving, it's like sheet action of all of this material will come into one area and then it'll wash down into a stream. And it is, soil degradation is the fastest way that we deplete nutrients for our farming. And it's usually a result of too much farming. It's not taking care of the soil properly. And then, of course, because we're irrigating so much, we salinize our soils, which means we actually increase the amount of salt, and that can accumulate over a long period of time. You end up without fertile soils, and you end up with areas where not a lot of things will grow because it's too salty. There are a variety of ways that soils also degrade. It's not just salinization or depletion of soil nutrients through extensive farming and improper use of irrigation. We have other pollutants. We tend to use an excessive amount of pesticides and fertilizers, and then we have oil and chemical spills often in areas, and once that happens, you can't use the land because, like PCBs, obviously they're called brown fields. You just got to leave them alone. Either that or you remove the overburden and put down new soil. But then you have PCBs that last, 50 or 100 years and do a lot of weird things to humans and other animals. So it's usually the case where companies don't properly dispose of their waste, and it ends up leaking out in canisters or whatever and contaminating the soil. Then, of course, we have compaction, which is pretty bad where there's livestock or there's the use of heavy equipment, where the soils get so hard that the plants actually can't penetrate them and they can't grow. And like I said, that's problematic if we need to eat food. Here's an extreme example of what happens when you do overgrazing, you deforest an area, and you excessively plow rather than plant fields and don't till them until you want to plant the next year. It'll keep the soil in place. As a result of poor farming practices, we had a dust bowl, or we called it the Dust Bowl, and that was Mexico, Colorado, Kansas, Oklahoma, and Texas, where we had severe wind erosion that's even going on today in some areas. If you go to Nevada, if you ever have a chance, be in Phoenix when they have a dust storm, it's pretty incredible. They're not pleasant, and there's a huge amount of wind erosion that moves a huge amount of material around. And people actually fled because they couldn't grow crops. They went out of business or they couldn't farm. And there was a huge migration out of the area in the 1930s and 40s when this was going on. So we have these, I talked about expansive soils that will expand and then they'll erode because the cracks open up or close up when it gets a lot of water, or they open up and you get a lot of that material falling into the crack, and it's a very mobile system. I mean, the soil moves around quite a bit. And like I said, it takes about 1,000 years to make 1 inch of good soil, and we lose about 3 inches a year. And here we have an example of someone contour plowing, which means they're following the natural slope and geography of the land. They're also using practices where they've separated specific water sources where it's the lowest point, so even when it runs off, they have a collection pool here. You can also use terracing and, like I said, no-till planting, which farmers are hard to change, or there are people that you really can't convince to do something different, which I get, because if you do something different and it doesn't work, you're out of business. And I grew up on farms, so I get that. But at the same time, you have to make sure that we take care of the land, because even if you want to farm and it's not healthy, you can't grow anything. So in conclusion, rocks and minerals disintegrate and decompose by a process of physical and chemical weathering, and organisms contribute to mechanical and chemical weathering through their activity. The parent materials transform into weathering products, which include ions in solution, water-soluble salts, insoluble solids, such as a clay mineral, and then they will precipitate out, and you get calcite formation, which will also increase the amount of mechanical weathering due to the growth of those crystals. So mechanical weathering enhances chemical weathering by breaking material into smaller pieces, thereby increasing the surface area for chemical reactions. Soils consist of weathered materials, air, water, humus, and also the plants which they support. We also need to be aware that we need to take care of our soils so they can be farmed long into the future. Thank you.